Hello, I am Dr. Vikas. Today we are to design a singly reinforced concrete beam. For that, we'll have to decide some parameters. First parameter is support width, which is taken as 200 mm. Clear span 4 meter. Support conditions. It is simply supported at both ends. M20 FE415. We are using this design by limit state method. For that, we have to go for the design load, and the design load is given as 20 kilonewton per meter. Now we'll go for the solution. Assume first of all the cross section. How to assume the cross section? The depth and the width. We call this as a cross section. The depth of the beam is calculated as per the IS code 456-2000, clause number 23, page number 36, in which it has been mentioned that if it is a simply supported beam, then it should be taken as span by depth ratio as 20. But considering on the safer side, because we'll have to apply for all types of checks, so we are considering span by 10 instead of span by 20. So span is 4 meter, that is 4000 mm, divided by 10, it is 400 mm. So we can say the overall depth is taken as 400 mm, and generally the width of the beam is taken half of the overall depth, that is 400 upon 2, that is 200 mm. And now we can see the cross section that we have decided in the beginning is 200 cross 400 mm. Now we have to calculate the effective span. All the calculations are always based on effective span. There are three parameters: overall span, clear span, and effective span. Outer to outer distance of a support is called as the overall span. Clear distance between the two support is called the clear span. I will correct, the overall span is nothing but outer to outer distance is called the overall span. Inner to inner distance of a support is called the clear span, and clear span plus effective depth of the beam, or clear span plus center to center of the support width, is called effective span. Now in our case, first of all we have to decide the effective depth. How to find out the effective depth? It is nothing but L plus, that is clear span, plus half the support thickness on either side, or we can call as overall depth minus the clear cover minus half the bar diameter, we call as effective depth. Now first case is clear span is 4 meter. Effective depth as it comes out to be 365, that is 0.365 meter. That comes out to be, and the last one is the L plus 0.2, that is 0.2, that comes out to 4.2. Whichever the least, now we can find that 4.2 and 4.365 means the effective span will be taken as 3.625 mm. The least of the two is, one is 4.35 and other is 4.2. So least is 4.2, and now you can see this figure. Effective span 4.2 and designed UDL is taken as 2.0 kilonewton per meter over the entire span. The maximum bending moment for a uniformly distributed load over the entire span L is WDLE square upon 8. where WD is taken as 20 kilonewton per meter and LE is taken as 4.2. Substituting the value for design load and LE, the maximum bending moment, that is MU max, is considered to be calculated and it comes out to be 44.1 kilonewton meter. Similarly, we have to calculate the maximum shear force. Maximum shear force, which is denoted by VU, which is nothing but the maximum reaction just to the left or right of the support. And as it is simply supported, uniformly distributed over the entire span is same, so VU is nothing but WD by 2. And WD is 20, LE is 4.2, divided by 2, it comes out to be 42.0. Hence, maximum shear force is 42.0 kilonewton. Now, after finding out the effective depth, after finding out the maximum bending moment and the maximum shear force, now we'll come across of finding out the effective depth. The D required is nothing but under root of mu max upon R into B, where R is nothing but 0.138 FCK. 0.138 comes out to be for M20. So FCK is 20, so it comes out to be 2.76. The B is nothing but the width of the beam and which is taken as 200 mm. Substituting the value of mu max and B and D, as everything is to be converted into same unit, so we are converting this 44.1 into 10 to the power 6 in kilo Newton mm, 2.76 and 200 mm, so it comes out to be 282.65 mm. Rounding it on the higher side, we can call that effective D is 300 mm. This is the required depth. How much depth we have provided? That we have to see, we have already provided 365 mm. We have already provided 365 mm. So D provided, that is the depth provided, should always be greater than the D required. And in our case also, now we find that the D provided, the depth provided is 365, and as per the calculations, D required is 300 mm. So D required is more than D provided, and we can see it comes out to be more and hence safe. Now we'll go for calculation of reinforcement. There are two methods for calculation of the reinforcement for the beam. One which is already given in IS code 456 page number 96 for finding out the area of steel, and another is an empirical formula, and that empirical formula is 0.5 upon Fy into Fck into bracket 1 minus under root of 1 minus 4.6 mu max upon Fck Bd square bracket close into B cross T, where Fck is 20, Fy is 415, mu max is nothing but it is 44.1 into 10 to the power 6, and from the calculations we find that the area of substituting all these values over here in this mathematical expression, area of steel is calculated and it comes out to be 372.91 mm square. Or I am just taking on the higher side, rounding it down on the higher side, it will be taken as 400 mm square. Now, we have to decide the bar diameter and the number of bars that is to be provided in the tension zone. Now, considering 4 bars of 12 mm bar diameter, So total area of steel provided is 4 bars of area of 5 by 4 d square, that is 12 bars. It comes out to be 452 square. Now AST provided is now 400 square is definitely required for that one, and calculated is now 452. We are providing 52 square and required is 4 square. As usual, provided steel should be more than the required one. So we can say yes, our design is safe for the reinforcement also. Now we'll go for the next part, the design of the shear reinforcement. Shear reinforcement that would be calculated in terms of the vertical stirrups. Nominal shear stress is to be calculated by using tau VU as tau U minus VU upon B into D. VU is 42.0 multiplied by 10 to the power 3 to make it in Newton. B is 200 and D is 365 mm. Tau VU is nothing but, substituting these values, it comes out as 0.57 Newton per square. This is the actual shear stress coming on a beam. Then we have to find out how much shear will be taken by the concrete. That can be calculated by using, first of all, the value of percentage of steel. Percentage of steel is calculated based on the mathematical expression as 100 into area of steel upon BD. Substituting all the value, PT comes out to be 0.62. Now, with the value of this PT, that is percentage of steel, refer table number 19 of IS code, page number 73, and you will find the table shows the value for 0.25, 0.50, 0.75 in terms of the percentage of steel. Mix is there, and the tau C value respectively given for 0.5 as 0.48 Newton per square, while 0.75 for same M20 is 0.56 Newton per square. But we are interested to find out value for 0.62 Newton per PT at 0.62. So interpolating, we can find the value for tau C comes out to be 0.52 Newton per square. Now, once we can find out that tau C is there, then we have to find out three important features. One is the tau C, another the tau V, and the maximum tau V. That is tau C, tau V, and tau C max. Then, according to the I score, there are three cases. Condition number one, when the tau V is less than tau C and also less than tau C max. Condition number two, tau V is greater than tau C but less than tau C max. And third important condition is tau V is greater than tau C and also greater than tau C max. Here we know that the tau V is 0.57, tau C is 0.52, and tau C max is 2.8 Newton per square. Now, tau V is greater than tau V is greater than tau C but less than tau C max. So we have to go for condition number 2, and using that condition number 2, we have to find out the balance shear taken by total shear minus the shear taken by concrete, which is nothing but Vu minus tau C BD. Substituting the value of Vu, tau C, BD, we can find that the balance shear for which we have to design the shear reinforcement, it comes out to be 4040 Newton. Rounding it on the higher side, say we can say that VUS is 4500 Newton. Now we have to design the shear reinforcement using the formula given on page number 73 of clause number 40.4, and that too for B. Now Fy, D, tau Vd and everything is given. We can find out the value of SV. It comes out to 16556 mm center to center, which is under any circumstances should not exceed 300 as per the code. So now we have to go for the what is the minimum shear reinforcement that is to be provided, and it can be seen that the minimum shear reinforcement provided by page number, which is already given at page number 48, that is ASV upon BSV should be greater than equal to zero point 0.4 upon 0.87 of Fy. ASV is the area of the vertical shrub, B the width, SV is the spacing of the vertical shrub, Fy as usual taken as 415. What is ASV? If we are considering 6 diameter of the bar with two legs, then we can say two-legged 6 Phi. The total area will be 2 into pi by 4 into 6 square. It comes out to be 56.56 square. Substituting this, the spacing of the vertical stirrup comes out to be 255.0 Newton per center to center. Rounding it on the lower side, not on the higher side. So it's we are reducing to 250 center to center. Now here you can see the figure itself shows that the top reinforcement bar we call as anchor bar, need not to design. The shear reinforcement of 4 bars are already given over in the bottom, and these are the stirrups of two-legged 6 Phi at the rate of 250 center to center. This is your L section and this is your cross section. This shows the 4 bars of 12 These are the 2 bars of 10 and these are the two-legged 6 Phi at the rate of 250 center to center over the entire length. So design of the shear reinforcement is carried out like this. Now we are supposed to find out for the check for development length, that is LD. As per the code, we have to go for the value of LD as 5 into 0.87 Fy upon 4 times tau BD. Phi diameter of the bar that we are using, that is 12 Fy already known as 415. Tau BD designed bond stress. As per the code, page number 43, for M20, tau BD given as 1.2. But as per the code, it should be increased by 60%. So hence it is taken as 1.2 into 1.6, that is increasing by 60% in case of the limit state, and it comes out to be 1.92. So this much required length of 564.14 required to be provided in the beam just to make the reinforcement and steel. Now, how much length we are supposed to provide? That can be calculated to m1 upon v plus L0. m1 upon v plus L0. m1 is nothing but the bending moment, maximum v is the maximum shear force, and L0 has got two values. One, effective depth or 12 times bar diameter, whichever is greater. This is already mentioned in the code. This is already mentioned in the code how to find out value of L0. M1 that we have already seen is 44.1 and this is 42. Substituting these values over there, L0 is 365 effective D or 12 times diameter, whichever is greater, and M1 upon V plus L0. But as per the code, it is to be increased by 30%. So it is to be multiplied by 1.3 and it comes out to 1730 mm. And now required is 564, provided is 1730 mm. So our design is safe for the development also. Now the first and the final check is the check for deflection. Check for deflection is nothing but from the mathematical expression given over here, actual deflection ratio when multiplied by the actual modification factor should be greater than actual span by actual depth ratio. Just to find out the value of actual modification factor, then again go to a curve shown on page number 37, in which there are various curves are there. We have to correct the second curve because we are using the Fy as 415. So it is to multiply by 0.58 already mentioned in the code note so far on the same page, page number 37. Then you will find that the 0.58 multiplied by 415, it comes out to be 240. So we have to select the 415 into 0.58, that is 240 curve. PT is already given as 0.62, and from this we can find that span by 20 ratio is already given as 20. So 4000 upon 400 is the actual span by actual depth ratio. This is the value of that we have calculated for actual modification factor multiplied by span bar ratio, that is 20 we started in the beginning, which is should be greater than 4000 divided by 400, that is 10. So it comes out 23. So modification factor times span ratio should always be greater than 10, so it won't fail in the deflection. And we find that the permitted deflection is 20, ratio is 23, and actual span by deflection ratio is 10. So it can't fail because of the deflection. So we can say the design is safe for the deflection also. Summarizing the whole beam design, we can say the beam cross section as 200 cross 400. Main reinforcement at the bottom is 4 bars of 12 mm and stirrups as two-legged 6 mm at the rate of 250 mm center to center. Effective span as 4.2. Thank you very much.